everyone, so today we're going to be doing this week's physics quiz. Now let's begin. So first question, it's telling us we have a pulse in a rope and it reaches its end, which is a free end, so it's free to move up and down a pole. Which of the following happens to the pulse upon reflection? Now I would explain this, but I feel like it's better when we see it, so I'm going to show you what they mean now. But let's first read our options. The pulse is inverted, the speed will increase, the frequency will remain the same. The wavelength will increase, the amplitude will remain the same. Let's see. So here I have a simulator that's going to show us how it looks like. So let's give it a pulse. I want you to see in slow motion what's going to happen. So it's going to go up, the pulse is going to travel, and it reaches the free end, it goes up. And then it's going to continue above the line. It's not inverted. Now when it reaches here, then it inverts. But when we want when it reaches the free end, will it invert? No, it will continue moving down. Like, see, it's now on the upper side and it stops there. See? It will go back while it's still up. And let's look at the amplitude. It started here. I'm putting my cursor on where it was. The amplitude, I don't know if you can see it in the video. And it will go down to the same amplitude. The amplitude will not change. The speed, is it changing? It's not changing. This is the normal speed. Does it look like the speed's changing? No. Is the wavelength changing? No. So in this example, is the pulse inverted? No. We saw that it's clearly not. Did the speed increase? Definitely not. It stayed the same. Will the frequency of the pulse remain the same? Yes, the frequency will remain the same. The wavelength slightly increases? No, the wavelength will not increase. It might even decrease if there's damping, but since we had an ideal case, no damping, the wavelength will not increase. It will stay the same. Amplitude of the pulse will remain practically the same? Yes, the amplitude did not change. So that's the first question. Moving on. Okay, here we have a plane wave striking a straight reflector. So it's gonna hit the reflector, and once it reflects, it's gonna reflect this way. And the reflections are always, or like the lines are gonna be perpendicular to the reflection. So this is the only correct, like, logical answer. You can memorize them from the book. Moving on. Okay. So this is a ripple tank, and you're looking at it from up. The oscillator is generating straight waves. What's gonna happen when this wave reaches this blank, or this hole? It's gonna diffract. Whenever you see a tiny hole or two holes by any chance, and a straight wave, you're gonna have diffraction. What's gonna happen to the waves? They're gonna continue like this. They're gonna bend. So this is how they're gonna diffract. Now moving on. Okay, look, whenever you have two pulses of equal amplitude, one is up, one is down, they cancel out and become a straight line. If both are up and they're gonna meet, they become a bigger one. That's it. This is called, now in this case, one's up, one's down, so it's destructive interference. This is constructive, because it's constructing, it's building upon it. Moving on. Okay, this came from last week. The loudness, whenever you hear the word loudness, it's talking about amplitude. Pitch, it's talking about frequency. Okay. What happens when pulses in the same sense meet? Like I just showed you now. They're gonna become one bigger one. Their amplitudes will add constructively. Now, if these were of the same amplitude, both of these, they'll add constructively, but they'll add constructively, and this will be 2 times whatever this is. If they're not the same amplitude, they're just gonna add upon each other. We're gonna see it in a later question. For example, I found this simulation also. Here you have two waves, one's traveling right, one's traveling left. I want you to see what's gonna happen when they meet. So now they're traveling, and when they meet, they're gonna add up to become 1. Now, let's see if they're different pulses. Now, this one's big, this one's small. Let's see what's gonna happen. They're gonna add up. They're not gonna become double, but they're gonna add up. And what's one thing you noticed? Also, this one was the big one. This one was the bigger one. When it came here, it remains the bigger one. It doesn't change, okay? Now let's see destructive, identical pulses and destructive. One's up, one's down, and they're identical. So what's gonna happen? They flatten out. For a split second, they'll become 0. Now if it's different pulses, they're gonna remain a bit up. They're not gonna fully straight line, because we know they're subtracting from each other. That's why. Now here, the correct interference between 2 identical pulses, this we just showed you, 2 identical and it's destructive, so they're gonna flatline only. Moving on. Okay. Which statement describes circular waves that reach a straight barrier? When you have circular waves and they reach a straight barrier, the laws of reflection are definitely obeyed because they're gonna reflect. The reflective waves seem to be coming from a point behind the barrier. Why? Because they're gonna reflect in this way. Like, let's say you have a source here and it's reflecting waves like this, and you had a straight barrier. When they reflect, they're gonna come like this. So it looks like they're coming from this direction. So that's why the reflected waves seem to come from a point behind the barrier. Now, the laws of reflection are not obeyed? No, they are. Circular waves undergo refraction? No, it's reflection. Moving on. Okay, here I told you, when you have like 2 slits and a narrow slit, it's gonna curve and they're gonna go outwards. This shape is gonna happen when you have 2 slits. When you have 1 slit, this is what's gonna happen. This one. This is when you have 2. Moving on. Okay, this was last week. We said we look at the one with the highest amplitude. This is the only one whose amplitude is at maximum, so it is the loudest. Now the highest pitch is the one with the biggest frequency, so the one that you have the most peaks in, which is D. So B and D. Moving on. Now here we have a question. The diagram shows some water waves and you have a gap between the 2 stepping stones. So this is acting like your slit. So what's gonna affect the diffraction of the waves? Density of the water has nothing to do with it, because the density of the water here is gonna be the same as behind the rocks. The type of stones don't really matter, because all the stones are helping you with is giving you a gap. The wavelength of the water waves, yes, if you have a bigger wavelength, you're gonna have bigger diffraction, and so on. The width of the gap, yes, I think there's also a simulator for this. I'll see if I can find it now. The amplitude of the water waves, not really. They don't really affect. Let me see if I can find the simulator. Okay, so I found this generator, or the simulator again. And so we're gonna have a straight and 1 width. So you can see what's happening. It's becoming circular. This is what's happening. Now, if we increase the frequency, what's gonna happen is they're gonna become closer together. Now, if we take the frequency back to middle and we decrease the amplitude, when we decrease the amplitude, as you can see, they're becoming more weaker. So when you have an amplitude, like the lines are more defined. Now, let's say we have 2 slits. See what's gonna happen? It's like you're gonna have a straight line that's curving like this almost. And that's it. Moving on, back to the quiz. So the wavelength of the water waves, so how much distance is between them is affecting, and the width of the gap is affecting. Oh, I didn't show you that part. Let's go back to 1 slit, and let's increase the slit's width. Let's see what's gonna happen. See, they're diffracting more widely. I'm gonna decrease it, and you can see what's happening. They're changing. Now, let's go back. The amplitude of the water waves did not matter. Now, which property changes with the frequency of the sound is increased? The pitch. When I told you, whenever you see the word frequency, you link it to pitch. Whenever you see the word amplitude, you link it to loudness. And whenever you see the word amplitude and sound intensity, this is equal, or intensity of the sound is equal to amplitude squared. So if the amplitude is doubled, the intensity is 2 squared, so it's 4. It's quadrupled. Moving on. Okay, this is constructive interference, where we have like the two different amplitudes. So like I said, when they're gonna meet up, like I showed you, they're gonna add on top of each other, and when it goes after, it's gonna continue normal. It's gonna continue like nothing ever happened. Nothing's gonna change. I showed you this, and this is called constructive interference because they're both on the same side, up. Moving on. Okay, here we have a sound wave, and it's set towards a concrete wall. The wave train reaches the wall at 0.20 seconds and reflects off of it. The diagram below shows the displacement time graph for the incident wave. Now, when you're reflecting the wave, what does reflecting mean? Reflecting means it's gonna just happen the exact same thing. So it's gonna do this and then this again. You're reflecting it. So this is your correct answer. Now telling you here it was reflecting, yeah? Now here it's refracting. Assume that the sound wave partly refracts. Whenever you have refraction, the two properties that will never change are frequency and period. Their amplitude is gonna change because you're refracting. You're going from one dense to less dense, or more dense to, or less dense to more dense. So amplitude is gonna change, wavelength is gonna change, and speed is gonna change because there's a bit of damping in the process. Now here, the wave can be classified as mechanical because you're throwing a stone in the lake. You're physically throwing it. Now it can be transverse because displacement is perpendicular. Whenever you see the word perpendicular, it's transverse. Now the wavelength to 1 decimal place. Now to find the wavelength here, they told you each small box represents 20 centimeters. To find the wavelength, count the small boxes. You have 4 small boxes. 4 times 20 is 80 centimeters. They wanted the question in meters, so it is 0.8 meters, and that is your wavelength. Now the speed of the wave. Now you're gonna say, okay, so it's just 0.8 divided 2.6. No, because read the question carefully. They said the stone is thrown and 2.6 seconds this photo is taken. So all this happened in the 2.6 seconds. So to find the speed, we need to calculate the distance traveled from the stone and then divide by the speed or the time. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So it is 16 blocks away. Each block is 20. So that's 320 centimeters, making it 3.2 meters away. Now when you put on your calculator, let me just do it really quickly. 0.2 divided by 2.6. Okay, so when you do 3.2 meters divided the time in seconds given, which was 2.6 seconds, 3.2 divided by 2.6 is going to give you a long decimal, but it rounds to 1.2 because they said to 1 decimal place, meters per second. That's it. See? So the speed is 1.2 meters per second. Now the frequency of the wave, what did we say about the, the equation from last week? Velocity equals frequency times lambda. Lambda is the wavelength. We have the speed, which is 1.2, equals frequency, which is what we're finding, times 0.8. So 1.2 divided 0.8 equals to 1.5 hertz. And that's how you solve this question. Let's move on. Okay, they're telling you have a small projection of a screen and it's shown below. What's this observation called? You could see that this is like a slit pattern. So what's it's happening? Whenever you have something like this, it's diffraction. Now, when you have the light fringes, what's gonna be happening? It's constructive. Dark is destructive, light is constructive. Whenever you see them, know them. Now, moving on. Okay, so this is your last question. The type of radiation whose wavelength is longer than visible light. So you have visible light, but so it's longer than visible light, but shorter than microwave. So it's between the two. Which one's between microwave and visible light? Infrared. You have to memorize them. They're in the book. We took them already, but in like a different way. They're gonna be radio, then microwave, then infrared, then visible, then ultraviolet, then X-ray, then it's ultraviolet, then X-ray, then gamma rays. That's your electromagnetic spectrum. Now here it's telling you have from air to water. So imagine it as a light wave. If it's a light wave and it goes from air to water, what's gonna happen? We took it last year. It refracts. What did I tell you about refraction? Frequency and period will always remain the same, whereas speed and wavelength will always decrease. Because, why is it decreasing? Because you're moving from less dense to denser. Less dense to denser, they decrease. Denser to less dense, they will increase. And that's it for this quiz. Hope you understood everything. Have a nice day. Bye.